Hello, everyone. Welcome to the eighth lecture on causality for AI and ML. Today, we will be talking about neurocausal models and how to apply them, how we can fuse classical ML and causality together. So, first, maybe have a look at the pros of classical machine learning applications. So, within the recent year, or rather the last 10 years, we saw that they are applicable to a wide range of problems. So, whenever we have sufficient data, we can try at least to train a machine learning model on it to solve certain tasks like classification, regression, and they can handle multiple modalities, so classical tabular data, textual data, image data. So they are quite flexible in what we can apply them to. Furthermore, the training process via backpropagation is quite straightforward. So usually we have a relatively similar training loop for all of our neural networks. And we don't really have to care that much about the underlying processes. Of course, there is a lot of engineering that goes into all of this, but like the base algorithm has stayed the same for a long time and is relatively easy to explain. And third, these models can handle large-scale data and large-scale domains. So we would like to maybe use that flexibility and these properties of classical ML models. In particular, here we are talking about neural networks, to make use of them in causality or use causality to improve these models. So obviously there are some downsides to classical ML models. So usually they do not generalize well out of distribution. So as we already have seen, they can like learn shortcuts. They are prone to confounding and so on. So because of that, the models are often trained on an associational level. That means they learn correlations. And if we don't like specifically set up our data in a way that makes them learn also interventional information, they usually are like prone to learning these shortcuts. And generally, we have no guarantees that they like act robustly out of distribution, that they don't learn confounding and so on. And here we might want to use causal models, SEMs or causal structure, to make them more robust against that. So, yeah, the question here and in this lecture is then, how can we counter these cons by leveraging causal methods and models? And maybe can we also scale causal methods beyond the small scale examples that we saw before? And that doesn't necessarily mean that we don't have, like we now scale to thousands of variables. We will also see that. But even using like modeling images with an SEM is super hard because images usually consist of 10,000s of pixels, and really it doesn't make sense to model every of those pixels as a causal variable because usually they have no semantic meaning in a sense. So we would maybe like to use autoencoders that group together or merge together certain image areas to get something meaningful, like get representations of objects, like the object color or shape, which then constitute maybe a causal variable that we can work with. So let's go ahead and look at first neuro-causal model, particularly causal normalizing flows. Normalizing flows are density estimators, which means that we train them usually on a bunch of data. And what we want to get out is not a classification or something similar, but if we now give it a new data point, we want to get the probability of this particular observation occurring. So basically, we want to learn the probability distribution over a set of data points or over some domain. And for this, normalizing flows are composed of a series of transformations. So usually they start with like layer-wise transformations, where each of those transformations is bijective and smooth, which has the implications that we can inverse all of those transformations. And so at the start, here we start at U in these images, but like what we observe are the axes on the right side of each of those graphics. So we start with axes, and here maybe for simplicity, first work in the reverse direction. So we reverse one of those layers, the last one in this case, and what we want to get out at the end at U is a distribution of standard normalized Gaussians. So Gaussians with mean 0 and standard variation 1. So, and there is a theorem that we can almost always do that under like particular smoothness and whatever conditions. So we take our data point, our data distribution, which models a particular probability function, and we transform this distribution, this density function, into a representation that only contains standardized Gaussians. So basically, we move the representation or reparameterize the coordinate space or the parameterization of that observational distribution into a space of independent Gaussians. So SEMs can be represented in various different ways. And the one we have mainly talked about before is the recursive representation, where variables each have a single structural equation. We feed a particular exogenous variable into it, and then also all of the parent values. And then we recursively, like starting with the source nodes, iterate through the network or through the SEM and compute all the variables one by one. So because we're talking about flows, it would be good to maybe think about how can we do things in parallel, because these flow models, usually we don't want to impose a particular graph structure onto them, because what they will be is sets of layers or series of layers that for every of those layers inputs gets a particular observation and outputs a particular set of latent vectors. And this input and output is usually done for every variable equally at every step. So instead of doing a recursive step, we can look at unrolled representations of SEMs. So this is on the second graphic here. And in particular, we can compute values of every variable at every time step. for this unrolling, but for the time steps where our variables are not yet computed, or where the parents of these variables are not yet computed, we just set their influence to 1 and propagate them just further down. So these are all the horizontal edges with a 1 on it, which basically means either, so it's the self-influence of itself on its own to the next time step. So that's basically saying we will keep the value that either comes from our exogenous variable, or we already have computed this variable and we want to keep now its value. And within these areas where there are red arrows, this is where we compute the actual value of the variable and not only propagate some intermediate values. So at the top you see, well, the first variable is a root variable without any parents, only from exogenous noise, and that gets forwarded. The center variable, then at the first time step, you see that the arrow, the diagonal is still 0, so we don't compute it because we first need to compute the top one. But in the second time step, we see that it still takes, via these horizontal values, its u value, but then also the first variable comes in with a factor of 2. And the same goes for the third, for the bottom variable. First, we only propagate the u value via the horizontal arrows. And then in the final time step, we compute its value. And at the last time step, then, we have computed all of the variable values and can output them as x. So then if we have this, we can, under some assumptions, so here for normalizing, causal normalizing flows, we assume that the structural equations are diffeomorphisms, so they are bijective and smooth. We can compress this unrolled representation back into a compacted representation, which basically means that we now take all these influences that get propagated through all of those arrows and push them together into a single operation. And under this diffeomorphism assumption, we can also invert this transformation. And this property is what we will use in normalizing flows. So standard normalizing flows are density estimators that apply a series of bijective transformations to transform a given probability distribution or a given density into a series or product of standard Gaussians. So Gaussians which are zero-centered and have a standard variance of 1, and they are all assumed to be independent of each other. And to make this like valid density estimator, these transformations need to fulfill additional properties. So what this normalizing flow usually does is we present it with a set of data points which represent our observed density. And at the end, at the output, we want to have our standard Gaussians. So we basically transform this density that we observe into a standard Gaussian representation. And along the way, we need to make sure, so since this is a series of transformation, we need to make sure that every of those intermediate representation, and also the Gaussians at the end, are still valid probability or densities. So what we need to guarantee is that with every transformations, the density still needs to sum to 1, or the integral needs to be 1, so we don't lose or gain any probability mass. And additionally, that all of those values are above 0. So we can't have negative probability anywhere. Basically, what this means is then if we have trained our normalizing flow, we give it a data point, like some configuration of variables. This normalizing flow will output us the probability of observing that particular data point, or rather the density of that. Yeah. So here again, this transform. At the beginning, we have some observation x. We apply our normalizing flow, and we obtain some u that then is parameterized or adheres to this standard Gaussian case. And usually, normalizing flows are defined the other way around. Usually, we say we have some u, which we might sample randomly then from those Gaussians, and we inverse our normalizing flows because we have said, okay, all of those transformations, they need to be bijective transforms, so we can inverse that. And then from these u's get an variable configuration, an observed variable configuration x. And yeah, more generally, so we won't go into this in detail, but basically what these transformations do is that they apply some sort of transform, right? So we need to go from our observed distribution to those Gaussians. And this is basically the standard formula, this reparameterization. We apply some transform, and then we need to adjust by the determinant of that transform at that place to keep the probability mass. So for numerical stability and so on, you've probably seen that before, we do all of those operations in log space. So this product that we have between the transformation and the determinant then becomes an addition. And yeah, during training, we just optimize. We have a layer of transforms, and we optimize the parameters of those transforms. So for causal normalizing flows, we will consider a particular type of normalizing flows, which are called autoregressive normalizing flows. And this goes back to this unrolled representation that we saw earlier, where at every time step, we output a bunch of latent, or in the end, the observed variables. But what we saw in those arrows, maybe let me go back. What we saw in those arrows here is that these arrows at every layer follow a particular structure. So there are no diagonal arrows going back up, but it's always going down from the top. So what this means is that, like, the first variable only depends on its own u. The second variable only depends on the first variable and its own u. The third on the first and the second and its own u, and so on. So we have a particular structure where we have a causal ordering, or assume a causal ordering, and this needs to be given to us for our causal normalizing flows. And then if we have that, we construct a series of those transforms where every transform for every of those first, second, and third variables only takes the value of its own u and the variables that came before it. So this is basically what autoregressive normalizing flows do. They have some more constraints, so a particular transformer which needs to be strictly monotonic, and then an additional conditioner. So this is basically that we not only take our own u, but we take all the values of the variables that were computed before us. And then we basically, for every variable, we get an autoregressive flow. These autoregressive flows are conditioned on each other and basically transform the observed density into these standard Gaussians. Yeah. And as I said before, this is exactly the structure of our unrolled or then compacted SEM if you consider the whole normalizing flow as a single transform. But yeah, this only requires the causal order, but it requires the causal order, so it's not that we can simply put all our observed data there and just let it run and it will figure out things independently. But at least we need to know in which order these variables occur in the causal graph, because we need to structure our normalizing flows according to it. Yeah. And then for causal normalizing flows, we want to have particular properties. It should obviously capture the observational distribution well. It should isolate the true exogenous variables and be causally consistent with the true SEM. And the authors of that causal normalizing flow paper prove that this is the case under particular assumptions. And what they do, and I will just briefly mention it, they relate structural causal models or particular these processes that behave similar to it as triangular monotonic increasing maps, which basically, if you look at the vector on the left, is basically exactly this kind of thing where we have a bunch of functions, each computing a particular variable or particular factor, and the first function only takes its own value to compute the next time step or the transformed representation. The second takes also its own value, but also that of f1 or x1, and then so on until like the last variable or the last function is computed by taking all of the previous values and obviously its own. So by construction, autoregressive normalizing flows are those kinds of triangular monotonic increasing maps. And the authors show also that it's always possible to monotonize an SEM. So basically, what this right part of the formula says is that all of those transforms, they need to increase in value, and via some reparameterization, this is only always possible. But here we just leave it that it is possible, and yeah, if you want to know more, please refer to the paper. So the theoretical results that we get are that the use, so our Gaussian noise, can always be identified up to component-wise transformation. So basically what this means is that we get the right ordering of use. So we do not mix up or like mix together certain use, but they are component-wise independent of each other, and we identify the right one for the right variable. The only thing that can happen, and which we can't really prevent, is that we might not be sure on the exact scale of that U. And the second property is that it's consistent. So if the use can be identified, then causal normalizing flows are consistent with the SEM. So this is then maybe the rather easy part. So if we have these U's, if we know we can infer those U's from observation because our CNFs are normalizing flows and they are bijective by definition or by construction, then we can just reverse this whole process and get back our standard observational data. And what this means to be consistent with the true SEM also means that we are truthful to interventions and counterfactuals. So as soon as we have established causal normalizing flows, we can not only compute and estimate observational data, but we can also estimate interventions and the probability or outcome of counterfactuals. So if we consider again this representation of unrolled or compacted SEMs, we might want to ask, okay, how do we apply interventions here? Because the problem usually is that if we apply an intervention, let's say for the second, so the center variable, we usually cut all the parents to that variable. But here it might be not so obvious on how to do that, because somewhere in that network, we somehow need to cut a bunch of arrows. And maybe if we have trained our causal normalizing flow, it's not really obvious first how to cut parent values, because our causal normalizing flows, so this transformation, they always assume that we give them some sort of variable value. And it's maybe also tricky to figure out the exact location on where we need to do this. So just replacing parent values with 0 might not be okay, because 0 might also be a valid value for those parent values, and so our transformation might not know whether we are in an observational or an interventional setting. What the authors propose instead is that instead of cutting arrows, we can just go and trace back the effects that an intervention would have on the latent variables. So basically the idea is, from an observational perspective, at least for the intervened variable, an intervention means, and we are talking about hard interventions here, that if we intervene on the second variable and we set its value to 5, on the very right of those unrolled representation, this particular variable will just be set to 5, and all the following and dependent variables on it will adjust their values accordingly. But since we are now in an autoregressive normalizing flow, what we can do is we go to our observational vector. We replace that particular second variable value with the interventional value, and then we reverse the normalizing flows for the second variable value. So basically, we are inferring all the U's that would have led to this particular intervened value. And now if we have this kind of thing, we can just forward our process again to obtain the intervened X. So maybe more formally, either we are given some observation and we first infer the use using the inversed normalizing flow, or we just sample a random U from our Gaussians. Then we obtain our observed vector in the first step. We intervene on a particular variable and set its value to C. And for that intervened variable, only for this one, we inverse the normalizing flow to obtain the intervened u for this. So we don't change any u above or below, but only for this we consider what would this u have looked like if we intervened on that variable. And now all the variables that come after it, they still have that observational setting, which corresponds to their particular noise value. But if we now forward our process, all those variables that come after will compute their normal process, their normal function, but they will take in this intervened ui value that we modified. And so all of those variables will now also react in a way to that intervened variable that we had before. So yeah, here it's the algorithm from the paper again, which basically is this. So instead of sampling u, as I said, you can also take an observational variable configuration, just run the forward transform once to get those u's. And once you have that, you take those, get these x's again, intervene on one of those x's, reverse this process, and then with this particular intervened u that you place into the observational u vector, you proceed with the forward pass of the causal normalizing flow. And the same can be done for counterfactual. So once we can compute interventions, we can do the same for counterfactuals. It's basically that we now take an observation, we compute its use, we intervene, we do basically the same thing as I told you before. And here it's a particular thing with normalizing flows. So it assumes that we have the full observations. So standard counterfactuals would also work for partial observations, but normalizing flows always need to have the full observation. So basically, what I told you before, this interventional setting from where we first have a full observation and then infer those u's instead of just sampling from u randomly or from those Gaussians randomly. This is now this counterfactual step because those observations are now serving as evidence. And in a sense, for normalizing flows, because we always need the full observation, those two things collapse. So now that we have seen density estimators, maybe in most cases we are not that interested in probabilities, but maybe we want to work on image data. And in particular, we might want to have some image reconstructions and have a latent space that somehow follows causal constraints. And for that, people proposed causal VREs, which are basically variational autoencoder, where we constrain the latent space in accordance to some causal models. And the benefits of VREs is that they are very good at capturing image contents in low-dimensional latent spaces. So basically, a VRE consists of a encoder which takes a particular image, transforms it into a latent vector of like a lower number of variables, maybe 100 variables, and then a decoder which takes this latent vector again and tries to reconstruct the original image from it. And then from the original image and the reconstructed image, we can compute a distance, for example, a simple L2 distance between the differences of any pixel value, and use that as a loss term to train this model. And under particular assumptions, we assume that this latent vector basically is a sort of bottleneck, and the model is forced because Z is so much smaller than the whole image dimensionality that the VAE needs to compress certain objects or shapes, colors, and so on into those set values, and therefore we get more semantic, higher level variables there that represent the image contents at a higher, more semantic level that we can maybe work with then. So for VIEs in particular, people usually make the assumptions that the set values are Gaussian distributed. And this might be a problem because we might say, okay, we want to just place or assume that those set values, they correspond maybe to our variables in our SEM. And the problem is if we assume those set values are independent Gaussians, it doesn't really fit to the assumptions of our SEM, because in our SEM usually we have variables which are dependent on its parents. So by definition, they are not independent of all the other values. But if we think about it a bit more, and maybe also think back to our normalizing flows, we had a set of variables within our SEM which are independent, and these are particular the exogenous noise variables. And another thing is here that if we set, for example, one set to some value, so we want to intervene on it, usually its effect don't propagate to its causal children. So if we intervene on, let's say, set 3, all the following set 4, 5, whatever, they don't change. We don't have a mechanism that propagates our intervention to these follow-up vector values. So as I said, we do not assume again that those set values represent our causal variables, our endogenous variables, but we again need to assume, or will assume, that those set values correspond to our use. Yeah. So again, I described this already. The process is usually this three-step procedure, and for causal VIEs, we now make a particular addition here. So the first and the last steps are usually the same, but first we take an image, we encode it into those exogenous noise variables. Then we take those exogenous noise and we apply a causal layer. And basically what this means is that here, instead of the encoder outputting the exogenous noise and the decoder again taking this exogenous noise, we apply within this latent layer or this latent vector our SEM. So basically what we say is we take those exogenous noise, we apply some transformation and get out our causal variable set. And within those causal layers, we can apply interventions and do whatever we want. And then our decoder is trained to take those causal variables, not the noise, but now the variables, and reconstruct our original image from it. And This causal layer basically does the same trick as the normalizing flows. So the authors there assume that we have a linear structural causal model, so we can again have a compacted representation where we compress all of our structural equations into a single matrix, and then we just need to multiply that matrix by our predicted noise terms to get set. And in this representation, what we can do is then to constrain those values within A, so A is learned, but because we know the structure of our SEM, we will force particular entries of A to be 0 so that it doesn't approximate some arbitrary graph, but the graph structure that we give it. And again, we need this autoregressive property. So basically, we solve for a set, and this then gives this I minus A transposed inversed E. Basically, what this means is that we have set on both sides, and we solve for it, and I is here the identity matrix. Yeah, and as mentioned, the last step then is to simply decode from this obtained set vector the image. And one small note, so this works quite well under all of those assumptions. So we already have access to our SEM. We know how things in the image behave and how they relate to each other. Maybe we don't know the exact weights on the edges, but those can be learned. But causal VAEs then allow us to create a machine learning model that respects all of our causal constraints, all of our structural equations, and then work on image data so that we might observe video streams or simple images and map that to our causal variable values. So the third thing I want to talk about are causal SPNs, which are density estimators. And the thing with all the prior models was that they work quite well. They are able to simplify image data to a set of causal variables. They are able to estimate the density of some observed distribution or some observed data. But with SPNs, we are also or mainly interested also in the speed and the inference time that we have for particular models. So first, SPNs are sum product networks, and basically they are DAGs which consist of, at the leaf, some simple probability distribution or parameterization, so Gaussian leaves or discrete distributions. And then those leaves get combined either by a sum or by a product of leaf nodes. And then once we have those merged nodes recursively, they get merged again by either a product or a sum, then again a product and a sum, and so on until we obtain a single node at the top, which then outputs the observed density or the approximated density or the likelihood. So SPNs have particular properties in terms of efficient inference. So estimating marginal probabilities and so on. And here we see a three-variable system, and for that we can simply use structural causal models, or like more generally Bayesian networks, to infer some properties or some probabilities given some observation. But maybe we have even more complex environments, so we need to incorporate even more variables. And as you may know, inference in this kind of settings quickly becomes sharp P complete. So we might start to care about runtime. So in also time critical domains like trading or something, or like autonomous driving. But maybe then we want to model a whole ecosystem. And then even if we don't care that much about runtime usually, those queries can take maybe days or weeks or even months to compute. So because we have so many variables, it might be super hard to actually infer like particular marginal queries or conditional queries. So basically those problems become intractable. So here's an example. Basically the full evidence case that's easy and fast because we just don't need to marginalize out anything. We just look at all the probability distributions that we have for A, B, C, D, and so on. Look at the conditional probability tables that we have in our SDM or our Bayesian network, and then just multiply all of this together according to the factorization of our Bayesian network or our SCM. A problem may arise when we want to talk about marginal probabilities. So that means we only have partial evidence. So we need to marginalize out all the variables for which we don't have evidence. And this might be very costly because now we need to sum over all possible values, so all possible value combinations of all those marginalized variables. And this like quickly grows very large because it's always a product over all possible values over each variable. And the same then goes for conditional probability queries, because there we again need to do the same. The denominator and enumerator basically are marginal probability queries with different sets of given or observed variables. And there we also, for both of those terms, need to marginalize out the variables. And that can become very costly. So in this example, it might still be okay, like 5, 10, even 20 variables might be fine on a normal PC. Maybe up to 50 or 100 variables. If you're lucky, if you observe a lot of those variables, you still might be able to reasonably compute it. But as soon as you go into the thousands of variables, you're definitely not anymore able to compute all of this in a reasonable time. So it basically increases with 2 to the n of unobserved variables for just the binary case, not considering like higher dimensional variables. So as I hinted a bit before, some product networks are graphical models with a particular structure. So in the standard case where we observe all of the variables, they calculate the joint probability distribution, but they have this additional particular property that they can perform marginal inference in tractable time, which basically means that like the runtime does not explode when some of those variables are not observed. And here this tractability is in the or this marginal inference property is basically in the number of edges that we have in the SPN. So there's no free lunch, obviously. If we have very complex densities, then our SPNs might grow very large. So we just have a lot of number of edges, but oftentimes we are lucky and those distributions or those densities factorize well. So we get a very compressed representation of our density, and therefore marginal inference will be fast. Yeah. Again, at the very bottom of those SPNs, we have leaf nodes, which are base distributions or Gaussians or discrete distributions. Then usually the first layer is a product node, which says or models independencies. So this means that on the left and the right side of a product node, we have independent sets of variables. This means also the variable sets that go into those product nodes from every of those edges is independent, so disjoint. And then some nodes are mixtures of distributions. Here it's the other way around. So it's a weighted sum of those sum nodes that go into it. And here the constraints for those sum nodes is that they now need to cover the same set of variables. So if I have on the left branch L1 and L2 representing probabilities over variables A and B, then I also need to have for L3 and L4 to be distributions over A and B. So L3 and L4 can both have A in it or B in it at the same time. Same for L1 and L2. But then the scope of P1 is the set AB. The same is for P2. It has the scope of AB because those are the variables from the leaf nodes. And a sum node is only valid if both of them then if P1 and P2 have the same scope, so to say. But yeah, for closer explanation on how they work, what we can do with it, I would recommend our lecture on probabilistic graphical models, which is also given in this semester. So these networks basically take or learn leaf distributions and then combine those probability values or density values via a series of multiplications and weighted additions. And this is usually fine, so we can model and approximate arbitrary density functions or densities with it. But to make them more causal, we again, as in the previous models, need to think about what does it mean to intervene on those on those observations. How do we model interventions within an SPN? And here again we have the problem that we no longer have those explicit structural equations, but we somehow need to show the model how to work with interventions from just a data point of view. So the idea here is that instead of simply learning a fixed set of factors, so what is learned in an SPNs are the weights of the sum nodes and the parameterization of, for example, the Gaussians at the leaf nodes, we will condition those leaf nodes and those weights in an ISPN, so an interventional SPN, on the presence of an intervention. So basically what this now requires is that those values for maybe the mean and the variance of a Gaussian in a leaf and the weights of a sum node are now generated by some other function that takes in the set of interventions that are currently active. And in the observational case, it's just that no intervention is active. Usually we encode those interventions as a one hot vector. So for every variable in our SCM, we just tell it, is there an intervention or not? Additionally, there can be a second vector which tells the network then which value we intervene to, or the variable is set to. But like in the most simple case, we maybe just want to assume, okay, there can only be a particular intervention on every variable, and we just encode whether that intervention is there or not. Yeah. But basically what this then corresponds to is having a neural net which outputs the parameterization of our SPN. And then once we get those parameterization according to the active interventions, we then simply do the same forward pass. So we put in all our observational axes at the leaf nodes and propagate them like in a standard SPN to the top to get our density estimate. Basically, what this then requires us is to train our SPN with interventional data. So this really means where before we needed a causal order or the causal graph, here we don't explicitly require the causal graph, but we require access to interventional data in order that the model and the neural network can learn the right parameterization of that network. And similarly, once we are able to approximate or estimate interventions, we can also extend it to counterfactuals. So this is the figure from the paper from Florian from our lab. Basically, what we need to do is we first need to have the approximation of the observational world. So maybe all the variables were observed to be all ones. And then we have this interventional view where we intervene on the variable B. And in addition to telling the network that we intervened on that variable, we also tell it which value we set that value. And now again, we can train a neural network for this setting with an observational world with an applied intervention that then constitutes the counterfactual world. We can train the SPN to approximate those counterfactual values. Here again, it might be difficult to obtain counterfactual data because we usually don't have it in our can't observe it in the real world, but there might be methods like propensity score matching, or maybe we already have an SPN or a model that approximates our dynamics, and we generate training data from that. And once we have those SPN, we can perform those counterfactual queries. And the main point here really is that it's about tractability, it's about performance, because if we are in the domain of thousands of variables, all those other methods will simply break down, while SPNs keep or can perform that inference still in linear time in the number of edges. And now, as the last model, I want to present neuro-causal models, which are basically the neural equivalent of structural causal models. And this basically has a lot of theory with it, and basically is also concerned of if we have some observational data, if we have a particular graph structure, can we create a neural version of an SEM? And is this neural version then guaranteed to approximate our true causal model, or guaranteed to converge to the right model that generated the original data? So this is from the paper, the Neuro-Causal connection, and basically they draw that connection between structural causal models and neural models, which we'll see now. Basically, what they do is that assume that we know the causal graph already, and we don't know the exact structural equations. And also we don't want to make any assumptions about those structural equations. So for example, the causal VIE assumed linear equations. But here we want to allow arbitrary structural equations. And for that we use an function approximator, and in this case, it's a neural network. And so we build up a graph of nodes, and every edge is then approximated by a neural network. Or particularly not every edge, because if we have multiple parents to a single node, we have a single neural network that computes the value of this node and takes in all the parent values. And our question now is, if we train on L1 data that we observe, will those neural networks that we have placed at the edges, or rather at the nodes, will those neural networks approximate the correct structural equation? Will we get back the correct structural causal model from it? And yeah, again, as I said, so here it's written more formally. It's the same as a standard SEM. We simply swap out the structural equations via a neural representation by a neural network, and keep all the rest the same. So we have some noise, we have some set of observed variables, and the structure of our graph is known already. And the question here is again about identifiability. So thinking back to the do calculus, it might be that we don't observe all variables, that we have some latent confounders. And the question now is, well, I don't have training data on you. I have this neural causal model, and here you again see the corresponding structure of the NCM and the SEM. And will my neural network still capture the right thing? That's the main concern of those models. And basically what we can think of, or maybe let me go back once, is that if we think back to the lecture on partial identifiability, we saw that identifiability might be linked to groups of neural networks in the not fully observed case. So identifiability basically means that whatever I do, like even under all my unobserved variables, I can identify the causal effect to some query. On the other side, if a query is not identifiable, I have a bit of freedom or a particular range of values that I can estimate with my models. So basically, I resolve this confounding error that I have here, or like the generally edges where I'm not sure about the direction, and I just look at all the possible SEMs, so where I direct this particular arrow, and consider what would be the worst or the best case, or rather the highest and the lowest effect that could resolve from those models under the observed data. So I just sequentially sample or generate all of the models that would fit my maybe unobserved graph or partially unobserved graph, and then train it or constrain it to the observational data that I have to approximate my structural equations. And identifiability in that case basically means that my upper bound and the lower bound of my effect estimates should be the same. If they're not the same, that means I have different values there, which stem from different realizations of the SEM, of the edges. And that means my true causal effect is somewhere in that range. And what the authors now argue is that if we observe for the higher and lower bound the same value, these SEMs are guaranteed to truly identify the correct or the right causal effect. So this might first sound or look a bit intimidating, but it's really very simple. So we do exactly this. But now from a more machine learning perspective. So in the first step, we define our neural-causal model according to the causal variables and the causal graph that we have. So this is basically setting up this graph structure and defining the neural networks. And then in the second and third step, we do two things. We have a particular, or want to identify a particular causal query, so y given do x. And we set up our graph in a way that we apply this intervention there. And we assume that we have a particular set of observed data. And now what we can do, because our neural causal model as standard causal model still put out a probability, or at least we can use it to estimate the probability. We train our NCM once in a way that it should minimize the probability of the data given our causal query, and once that it should maximize the probability of our causal query given our observed data. And if the causal effect under that intervened graph is identifiable, then the authors show, or rather prove, that both of those optimizations, so once maximizing, once minimizing, they will converge to a single value, because by definition of identifiability, this is the only chance that the model has. So there is no room for like lowering or highering that probability value. If we have an unidentifiable query, so those two probabilities do not match, then we get two different values, right? So then basically we get exactly this higher and lower bound. And the authors here propose then to say, okay, the algorithm failed, or the identification of our query failed. But if they are the same, we know it's the exact identified answer to that causal query, and we will return the minimum or also the maximum. They are the same either way, so we get that value. In practice, here the authors talk about like exact inequality. Like in practice, it's due to training noise, due to sampling noise, and so on. We might allow for small errors and then maybe take the average of the minimum and maximum to return. And still, you might wonder, well, what if the minimum and maximum it is not identifiable, but these bounds are very close together? Then the authors argue that that's might not be that bad, because if the bounds are close together, we make less of an error. So we are still approximately correct in that case, but like in the formal, theoretical, like optimal case where everything works out well, where we don't or can disregard noise from sampling and from data or the training process itself, this theory holds or this result holds. So in this lecture, we have seen neuro-causal models. Some are concerned with reapproximating the density function at all, and make neural models able to apply interventions and also compute counterfactuals. Then we have seen causal VIEs, which are a way of handling causality in image data, also under or with the benefit that we can apply interventions and also maybe compute then counterfactuals. Then we had a look at interventional SPNs and counterfactual SPNs, which are more concerned with large-scale models. And finally, we looked at neural causal models, which are really like the neural equivalent of structural causal models. And all of those had the benefit that we could train them with standard deep learning, machine learning techniques, basically that they can all be trained with backpropagation, which might be nice because maybe we don't want to only use those models standalone, but integrate them in a like larger framework. And all of those models are helpful because we can integrate them seamlessly and do an end-to-end optimization without having to switch back to standard SPNs, which might be reasonable in the standalone case. If we already know the SPN, why not use it? But in like larger AI applications or systems, those models allow us to plug in those neurocausal models, use standard learning technique, and still obtain all the benefits that we get from causal models that we know from robustness results and generalization results of causal models. So yeah, then there are further works beyond SCMs, causal constraint models, and also not all causal inference is the same, which go a bit more into this discussion when to use which kind of model with particular benefits and so on. But yeah, I hope you got a brief insight on what is possible, what can be done. And in the next lecture, we will also look at causal representation learning, which is then even a bit more deep into ML and representation learning, because here we usually assume that we have access to a structural causal model, the causal graph or causal ordering, but maybe this is information that we do not have in usual real-world scenarios or like everyday applications. So in the next lecture, we will consider which types of assumptions on the data or on our model we can make to even identify causal effects without all of those prior knowledge. And that's it for this lecture. Thank you and see you next week.